Okay, so we're going to be learning about inverse relations and inverse functions. So let's start out with the definition of inverse functions. F and g are inverse functions if and only if f of g of x equals x for all x in the domain of g, and g of f of x equals x for all of x in the domain of f. So what in the world does that mean? Pretty much what that is saying is f of x and g of x are inverse functions if they literally undo each other. When you substitute one into the other, they literally undo what was done and they strip each other down just to be x. So let me just kind of shorten that up. If f of x and g of x are inverses, or if f of x and g of x are inverses, when you substitute one function into the other, it'll undo everything that was done, and you're going to see this in a minute, and you're left with x, and vice versa. So they literally undo each other. All right, the whole idea of an inverse is what one function has, the other has the inverse of that. So what is x on one function is y on the other, and what is y on the first function is x on the other. So the domain and range switch, and you're going to see that as we go through our lesson. Graphically, how we can tell if two functions are inverse functions is they'll reflect over the line y equals x. So let's put this together. Determine whether f of x and g of x are inverse functions using the definition of inverse functions. Then graph both functions. All right, anytime it says to prove or it says using the definition of inverse functions, this is where you're going to go back to the very top of your page, and you have to do the f of g of x and the g of f of x to show that they both strip each other down to just be x. So let's start again, just like our lesson from the day before. I'm going to use the different colors just so we can see it. So we're going to figure out what is f of g of x. Okay, so we have 6 minus 2, because that's our outer function, and there's our x, so we're going to substitute our inner function in where we see that. So we're going to put 6 minus x divided by... All right, so we got to clean this up, and what's going to happen is this 2 on the outside and this 2 on the inside right here, they're going to end up reducing. So then we are left with 6 minus, and you got to distribute that negative to both terms. So it might be good to just kind of still write it out like this. Then that's 6 minus 6 plus x, because you got to make sure you subtract both of them. And then we can see that these 6's cancel, so we are just left with x. So that worked. However, you have to prove it both ways. You can't just do f of g of x and go, oh yeah, they undid each other, and we have x. You have to do it both ways to prove that they are inverse functions. So now we're going to do the opposite. We're going to do g of f of x. So what that means is we're going to take our f of x function and substitute it into the g function. So that is going to give us 6 minus, here's our x, so that's where we're going to replace it with f of x, which is 6 minus 2x, all divided by 2. And then use your order of operations to simplify this. So in the numerator, we're going to have 6 minus 6 plus 2x, because when we subtract a negative, it becomes positive. We've got to distribute that minus through, divided by 2. We can then see that their 6's cancel, so we are left with 2x divided by 2, which is ultimately x. So when we did this, they both checked out. The first one became x, the second one became x, so we have just proven that f of x and g of x are inverse functions. Now we're going to graph them. All right, so these are just lines. Starting out with the first one, we have a y-intercept of 6 and a slope of negative 2. So we're going to graph this line. And label this one f of x. And then our other one is also linear. And if it helps you, you may want to just rewrite it so that you can see that y-intercept and see that slope a little better. So g of x is really 6 divided by 2 is 3, and negative 1x divided by 2 would be negative 1/2 x. So this one has a y-intercept at 3, and a slope of negative 1/2. So we're going to go down 1, right 2. And graph that line. And we will label this one g of x. Okay, then I am going to graph the line y equals x, because that is what we want to look for. If these two functions are truly inverse functions, they should reflect over the line y equals x. So what that means is if we were to fold our paper along this line, these two graphs should come together perfectly. They should be a mirror image, a reflection over that, and we can see that they are. Also, if you have a function that is going to intersect its inverse function, they will intersect on that line. If you ever are testing to see if two functions are inverses and they intersect but they don't intersect on that line, something's wrong. All right, so we've looked at this from an algebraic standpoint, checking to see they are inverses. We've looked at it graphically. Now I want to look at it numerically. The whole idea of an inverse is for every point xy you have on one function, the inverse function should have the point yx. So look at some of the points on f of x. We have 0, 6 and 1, 4. Look at your g of x line. We have 4, 1 and 6, 0. That is another way that you can check or help graph two inverses. You can take all the points on one of your functions, switch them, and then graph the switched points, and it'll graph your inverse function. Okay, remember, pause the video at any time to get down notes that you think you may need. All right, so let's try this. Apply the definition of inverse functions to determine whether each pair of functions are inverse functions. So all we're doing here, guys, we're just taking, doing what we did right above. You're going to substitute each function into the other function. And if they both come out to be x, we know that they're inverses. If they do not, there's no reason to even try the other one, because if one of them doesn't come out to be x, it is definitely not an inverse. And if you want, you can use your graphing calculator or Desmos and graph them and graph the line y equals x to check to see if you think they're inverses from a graphical standpoint. But when it says to apply the definition of inverse functions, you must use your algebra. Pause the video, try both of them, then restart the video. For the first one, we can see that when we do the composition of the functions, that they both strip down to nothing left but x. So they literally undo each other. The opposite operations undo each other, and they are inverses. Let's look at this graphically. What I've done is I've graphed each function separately, and then I've graphed the line y equals x. Remember, in Desmos, you can always click on this, and you could change this to be dashed if you wanted, just to show that that's that line y equals x in there. In this case, we can see there is that reflection over y equals x. These are not going to intersect. They are parallel lines. So understand that a function does not have to intersect its inverse function. It's just if it does intersect its inverse function, it would be on that line. The second one, we can see that when we do the composition, it does not come out to equal x. Once you realize one of them doesn't equal x, there's no reason to do the other one. These are definitely not inverse functions. If we look at them graphically, we can also see that they are not inverses. They do not reflect over the line y equals x. Also, they intersect, and they do not intersect on the line y equals x. So therefore, we know they are not inverse functions. Recall, a function is a relation in which each input, each domain value, is paired with exactly one output, exactly one range value. And remember that graphically, we can use the vertical line test to see if a relation is a function. All right, example 2. Find the inverse of the function and tell whether the inverse is a function. So if we're looking at this numerically, all we have to do to find the inverse is we just switch the points around. If we have the point 3, 2, we'd have the point 2, 3. And then we'd have 4, 1, 5, negative 5, and 3, negative 1. And then we're supposed to tell, is this a function? Well, if you were to graph these points and drag a vertical line across, you would see that that vertical line only passes through one point at a time. Also, you can look and you can see that none of these x values repeat. So each x value is paired with exactly one y value. So yes, this is a function. For the second one, we would have the point 4, negative 1, 3, 3, and 4, 2. So in this case, this inverse relation is not a function. It's not that it's not an inverse, it's just that the inverse is not a function because you have the point 4, negative 1 and the point 4, 2. So that x value of 4 is paired with two y values. If you graphed these points, you would also see that it fails the vertical line test. So in order to know if a function has an inverse that is also a function, the original function has to be what we call one-to-one. So what that means is each x value is paired with exactly one y value, but also each y value is paired with exactly one x value. Graphically, we can tell if the original function is one-to-one if it also passes a horizontal line test. So, of course, we use the vertical line test to make sure it is a function. But if it also passes a horizontal line test, then we know that the function is one-to-one, and its inverse will also be a function. So the existence of inverse functions. A function will have an inverse that is also a function if and only if it is a one-to-one function. All right, so property of inverse functions. Suppose f and the inverse of f are inverse functions. All right, so we've got some new notation here. So when you see right here this f raised to the negative 1, because that's what it looks like, that little negative 1 symbol actually stands for inverse. Anytime you see that in that exponent position on a functional notation, it means the inverse of. So instead of saying f to the negative 1, you're going to say the inverse of f. That's how we read it. It's just a notational thing. So if that is true, then f of a equals b, if and only if the inverse of f of b is equal to a. So what that's saying is, on the original function, if your domain is a and your range is b, then on the inverse function, the domain will be b and the range will be a. That's pretty much what the property of inverse functions tells us. All right, so how do we find an inverse function? What if we're just given the original function and it says, what is its inverse function? It's pretty simple. It's two little steps. Step 1, you're going to switch x and y. If your function given is given in functional notation, I just replace f of x or g of x or h of x, whatever it is, with y just to make it easy, and then change it back in the end. All right, then 2, solve for y. Okay, so let's look at this first one. It says, find the inverse of f of x. Then verify that f and the inverse of f are inverse functions and graph both functions. Well, I'm actually going to start out by graphing this function. So we have the function f of x equals 3x minus 2. So it has a y-intercept of negative 2 and a slope of 3 over 1. And it's just a little linear function. We will actually be finding inverses of all kinds of functions, but we'll do it as we go through and learn the functions throughout the semester. We learn how to find an inverse first, so that way as we go through different units, we can just pull up what we're learning now and apply it to the new functions that we learned. Okay, we can see here that this linear function is one-to-one. It's a function because it passes the vertical line test, but it's a one-to-one function because if you drag a horizontal line up and down it, it also only passes through one point at a time. All right, first we're going to find its inverse function. So to do that, I'm going to write it down. F of x is equal to 3x minus 2. And I'm going to first replace this and put y is equal to 3x minus 2. It just makes it easier as we're working it out. All right, so the step right here is we're going to switch x and y. So wherever we see y, we're going to put x. Wherever we see x, we're going to put y because that's the whole idea of an inverse. And then once we do that, we're going to solve for y. So to do that, we would add 2 to each side. So we get x plus 2 is equal to 3y. And then we would divide each side by 3. We get 1/3 x plus 2/3 is equal to y. Now, because this original function started out with functional notation, we want to make sure we always write it with the proper notation. We're honor students. We need to make sure we're using the proper notation. So we say the inverse of f of x is equal to 1/3 x plus 2/3. And that is our inverse function. The next step says to verify that they are inverses. So to do that, we're going to do f of the inverse of f of x. This is where we use our definition. So what that means is we're going to substitute our inverse function into our original function. So that's 3, and then where we put our x, we're going to substitute the 1/3 x plus 2/3 minus 2. We would distribute, so 3 times 1/3 x is just x. 3 times positive 2/3 is plus 2, and then we still have minus 2. Positive 2 and negative 2 cancel, and we get just x, which is the whole idea. Remember, a function and its inverse should undo each other. And then we will check it and make sure it works the other way. So we're going to do the inverse of f of x. So that is going to be 1/3, and there's our x. So that's where we'll substitute the original function, 3x minus 2, plus 2/3. So 1/3 times 3x is 1x. 1/3 times negative 2 is negative 2/3. And then we have that plus 2/3, and the negative 2/3 and the positive 2/3 cancel, and we get, in the end, x. So by doing that, we have proved that f and the inverse of f are truly inverse functions using the definition of functions. All right, now we're going to look at it graphically. So we're going to go over here and we're going to graph the inverse function. Now, some of y'all might be like, oh my goodness, it has a y-intercept of 2/3. That is going to be difficult to graph. So, guys, remember, you don't have to use the y-intercept to start graphing it. You could use any point on this, this line. Just find another point. Or you can use the fact that you know that every point on the original function, all you got to do is switch it around to get an inverse point. So, for example, this original function has the point 2, 4 on it right here. So then I know my inverse function is going to have the point 4, 2. So I could go get that point, and then I can start using this slope of 1/3. Okay, well, from there I'm going to go up 1, right 3, or I go down 1, left 3, down 1, left 3, down 1, left 3, and then you can check it. When you graph your line, it should cross that y-axis at 2/3, which it is going to. Remember, graphically, our function and inverse function should always reflect over the line y equals x. I always graph it as a dashed line because it's not part of the functions that I'm graphing. It's just there as a check. And, check your points. We're totally rule of fouring this. Remember, rule of four is where we look at things graphically, numerically, algebraically, and verbally. So we've got our steps on here, we've got our algebra on here, we've got our graph on here, and the numerical pieces where we're looking at these points. And you can pick any point on here, switch around, and make sure that the inverse point is on there. For example, this graph right here has the point -1, -5. Well, if we look over here, this one has the point -5, -1. Okay, so here's one for y'all to try. Last problem. Go ahead and try it, and we will go over it tomorrow. And even though this one doesn't state all the steps as the one above, I would go ahead and do it just to get that down pat. Find the inverse, verify that they're inverses, graph it, look at it numerically, look at it graphically, look at it algebraically, go through all those steps because that's really going to help you see the big picture. Good luck.